and an interactive timeline where you can listen to our catalog and tell us about your own car jobs.
Okay, and then there's 6.21 or how many meters? How many miles?
Sitting in the morning sun, I'll be sitting when the evening comes, watching the ships roll in, then I'll watch them roll away again. Yeah. Sitting on the dock of the
Okay, guys, let's go.
watching
You
the
have 2 minutes for your warm up.
roll.
2 minutes per problem.
Sitting on the dock of the bay. I left my home in Georgia, headed for the Frisco Bay. I've had nothing to live for, look like nothing's gonna come my way. So I'm just gonna sit on the dock of the bay, watching the tide roll away. Sitting on the dock of the bay, wasting time. Look like nothing's gonna change. Everything still remains the same.
Alright guys, wait. Don't need to discuss this so much. We have a test over next time. We should know how to do this. What's that? I can't even see your vision left.
I honestly have no idea. 32.
You don't give answers.
Alright, and Joy, do you also have your balloon drop stuff last time?
No, I have
Okay, so
Alright, Ray, what about you? We're testing. Quick. Nothing? What about you? No pendulum? Ladies, we have our pendulum. Do you have your pendulum?
Here. Don't steal anything else but
Alright, so let's take a look at Ready?
I don't know how.
But once you start, you get really big grade points. Write them down. The best thing to do is, if you want it, remember you can read it. Yeah, keep it.
Who got that one?
It'll teach you.
That was a year ago. I changed it, but
2 minutes, 1 minute. Right now, I'm ready.
Anybody have their balloon drop? All it is the time, distance, and velocity.
And then eventually, you want to start
I got 25.0.
That's all.
We'll do the tomorrow. Yeah.
It barely ever happens. Like, no, that's not true. My brother, but you can extend. You can extend your you like
Unless you gotta finish your pendulum data, and then you need to do the balloon drop test.
Dude, the worst thing is it happens when you're renting. So he was lucid dreaming, and he like realized he was dreaming, and in the morning.
All right, 5 minutes. Warm up. 5 more minutes.
In the morning.
Does anybody have their
In the morning, lucid dreams, and I work with That's impossible. You're not controlling it during the dream. You never knew that you were going to go in the right direction. I got it.
Oh yeah, that's when they were talking about that.
Because 75 times 6 times 50 and 50 times 6
It's possible, but it's not. You can't like be each other.
Did you all done?
I have one question.
I want to see it.
Wait, is this a female for this? Is this a
Anything today?
No, this is the distance it's all.
1 minute. Shut it down. 1 minute. All right, let me do a very quick. Wait, I'll take pictures. Let's take a quick look, guys, at what's coming up. If you're not submitted yet, keep going. Let's take a look. quick thing. Number one, you know you have a test next class, right? It's going to be over speed, velocity, acceleration, distance of falling object, velocity of falling object, and momentum. Graphs, labs, all the things we've done so far since we came back from Christmas, right? You have a motion and forces worksheet that you did that's due today, right? You put in the basket. There's a new one. There's a new one coming out today that will help you get ready for the test. Okay, so that will be the next class as well. For those of you that are Miss Dickey's study lab, Science Source is due for you guys on Friday.
Is it just having it over here?
Right here. Read Science Source 124, 128, 150, 162. And then don't forget, everybody has a science documentary due on Friday. The book is right there. Amazon.
They have it half price.
Do they have it at Great. Okay. Let's take a quick look. If you're not finished, submit. I'm going to pop this in. We have 2 labs to do today that are very quick, but I want to go through. Let's hop through this. I think this will be a good review for you. Let's go. Submit. We're done. Yep. This is just a quick review. It's not a grade.
Yeah, I'm just gonna put in a bunch of numbers.
Wow.
Well, I mean,
missed number 4.
it's only one of them. There's no way.
So there's not even 8,000. What if I take a while of this and find out? That'd be 800. That'd be, whoa.
All right, here we go.
Pretty sure that's not right on.
All right, I need everybody to stop down. You've had your turn, my turn. Will you please listen? Boys at this table have seats. Here we go. First problem. Convert 8 kilometers per second to miles per hour. Now, notice.
That's 0.
Can't really do this when y'all are speaking.
Oh, I entered
Ready? Notice I didn't put meters this time. Don't I normally put meters? So I let you skip a step, and the step was divided by 1,000, right? Because we normally have to go from 8 meters divided by 1,000 to get kilometers. So I gave you the kilometers already, but I also wanted to check to see, are we just randomly putting in that formula, or are we actually thinking our way through it? We'll figure that out in a second. But if I got 8 kilometers per second times 60 seconds times 60 minutes, cancel out my units, and that gives me, well, I still need to go times 0.621 miles per kilometer. By the time we cross out all of our units, it gives us miles per hour. Now let's just double check our answers and see where we're at. Okay, I got U7, got it really well. I would give, okay, Francie, sorry, and Red, you did it right, but you also divided by 1,000, right? So you forgot that step. I'm guessing that Maya and Dasha and you guys are doing the same thing, but you're using a different conversion, not 0.621. What'd you use?
I use one. I use one.
I used the wrong.
Did you divide by it or multiply by
I
it?
did the other way. I didn't.
Can't. You're going, then your units will be on the wrong side.
I used the wrong
other way. Instead of doing the 0.6,
Yeah,
I did
that's right.
miles per hour to kilometers instead of kilometers.
Okay. And so there's a whole bunch of you with just some crazy random numbers.
Yeah, that's the
All right, let me just tell you what we're going to be doing tomorrow. When we do this on the test next time, I'm going to be giving it to you in meters per second. You need to go miles per hour. You're going to have to take it times 60, divided by 1,000, times 0.621. Pop that in. That's going to give you in miles per hour. All right, now we want to make sure that we practice this and go over it a little bit more. We've done it 4 or 5 times, but just look at these again. See where we would have made a mistake, but we got to move on today because too much else to do. Let's take a look at this one. 8-kilogram missile was launched 4 meters per second upward. How many newtons of force is that?
I got that by
Did you? All right. We know last time we found out that force equals mass times acceleration. 1 Newton of force equals 1 kilogram of mass times 1 meter per second of acceleration. So if we look at that, don't we just have to take the 4 times the 8? How come I can't just take the 8,000 grams and say every 100 grams equals a Newton?
Then you have to take it for the acceleration.
The acceleration is not 9.8 this time, is it? So if it was like a gram scale and I picked it up and it was 8,000, I would say, oh, it's every 100 grams it'd be 80, right? But here I just take the mass times the acceleration, and that gives me 32. So take a look at our answers, and I'm looking at only 26% of you. Okay? Now, here's the good news. We just introduced this last time, right? Several of you are absent, some of you are still struggling with it. I'm not going to put any of that on the test next time. Okay? So if you're struggling with it, I would recommend starting to read chapter 3. Chapter 2 is all about the motion, chapter 3 is about forces. But this one, it's all about knowing what mass we have in kilograms, what acceleration we have here in meters per second. Number 3. Question. Number 3 is a momentum problem. We know that momentum is mass times velocity, right? On a momentum problem, we just take how much something weighs times how fast it's going. And when we look at that, we see that 50 times 10 equals 500, 75 times 6 equals 450. Big one wins, knocks the other one backwards. Right? So if the big one wins, we got most of you going here. All right, Logan, you got it right. You just didn't put the right capital letter for east, like we showed in the example. Arnold, you have a bunch of numbers and then an E. I don't know if that was like.
Oh, I got part of it.
And then Annalise and Carter. Why west?
I thought it was far away.
So you would just wait?
You got a 50-50 chance.
Okay. You do, but well. So in a momentum problem, remember it's not how much it weighs, it's not how fast it's traveling, it's the sum of those two, right? How fast they go. That's product.
Check my answer for number 4.
All right, number 4, a ball falls from the roof for 8 seconds. How far does it fall? D equals 1/2 AT squared. Again, how many times have we done this problem so far? 4, 5, right? Only thing that ever changes, the only variable here is 8, right? Okay, so half of A, what's A always going to be? 9.8. Half of A is always going to be 4.9. 8 squared is 64. 4.9 times 64 is?
Look at my answer.
Wow.
Wait, can you check my answer?
Nice. All right, I'm going to guess that Damien and Carter are using velocity, not distance formulas. And Annabeth, were you in a hurry? Just put your decimal in the wrong spot? All right, Everett.
Yes.
You and Teresa and Cameron, what are you using to get that? Did you not do the half?
I had the right answer, but then she told me something else.
So you just did acceleration times time.
Explain how we got that answer, Teresa.
All right, last one. Most of you seem to get this on a V over T graph. Straight horizontal line means constant speed. Look at it and analyze it. 50 miles an hour, 50 miles an hour, 50 miles an hour, 50 miles an hour. If your speed never changes, your speed is constant. But what happens here? Then it would not be above the origin. Oh!
Wait, then there would be no movement.
All right, let's take a look at our lab today. The first lab. If it was on the origin, it would be. All right, now I have to speed things up today. I'm going to give you guys a sheet with these things on it, so we don't have to copy. We are going to do 2 labs today, and I want us to go really fast because we have an early dismissal today. Okay, so friction. Sometimes friction is good, sometimes friction is bad. If you're walking on an icy sidewalk, you really want better friction, don't you? If you're playing on a muddy field and you want better friction with your cleats, if you're driving on the rain and the sidewalks, you want more friction. However, if you have an engine and you're running low on oil and those metal parts start rubbing together, you want a whole lot less friction, don't you? If you're if you're running around and you scrape your knee on the carpet and you get a carpet burn from the friction, friction is not necessarily a good thing. So, we're going to look at today at variables that affect the amount of friction we have. So I've got your variables on here. Let's take a look at our materials. We just need boards, 200-gram weights, spring scales, and sandpaper. All I need you to do is, number one, take your board at your table and measure the length, the width, and the height. Measure the length, width, and the height. You should have a ruler. That's not a board.
Wait, oh.
You guys have another board at a table?
Inches?
All right, so measure your length, width, and height of the board. Here's the boards over here. Now, from that, you're going to calculate your surface area for side 1. Then you're going to calculate the surface area for side 2. Length times width, length times height. Put those in your data table. I know you're all cutting, I know you're gluing, but I also know you don't hear me when you're doing those things. We need to measure length and height and width, and then calculate surface area. As soon as you have those, add those into your data table. Length, width, height, calculate surface area 1 and surface area 2. Then, after you've got your background information, I want us to then take our board, take your board, and then we're going to drag this on the table, just like we did on the Newton lab last time. But instead of hanging weights, we're going to be dragging them sideways. Measure how many newtons of force it takes to drag this. Then we're going to switch up our variable, and we're going to drag it across the side. Okay? So when we drag it this way, we're using the large surface area. When we're dragging it this way, we're using the small surface area. We're trying to find out if surface area is a factor that affects friction. Does a board actually take more force to pull from this side than this? We'll find out. The second thing I want you to do is find out what factor weight is. If you take a 200-gram weight and you put it on the table, and now we drag it in, and we take it and we pull it again, will it take more force or less force? Finally, we're going to check texture out. So we're going to add some sandpaper. Add one piece of sandpaper to the side that you're pulling and duct tape it down so that you can drag with a rougher texture. Then take another sheet of sandpaper and duct tape it to the table. That way you're going sandpaper against sandpaper. You may have any questions about what I'm doing? You have 10 minutes. Ready, set, go. All right, have you guys checked in your well, it's independent. You just checked it? Oh, yeah. Charlie, did I get you guys labs yet?
Length and the width.
Pencil lab.
Oh, okay.
Have you guys ever turned into motion?
Wait.
So we get the TV done.
We drag it.
Show me in pencils first.
Yeah, I guess you
How's your Joel?
then was that a demo when you got the water? We have to have that written down.
Okay, do you have your stuff on my side?
I have to video that.
Do you think this one's better?
Okay, let's do this one. This one's not rough. And my hands are
Arnold, what's your shoe say?
It took me 3 seconds. It took
No, you have to put the...
I'll call it.
Yeah, put it on here.
Oh, we're using. It took 3 seconds. So, yeah, it took you guys.
Oh, it's okay.
Well, then you have to do it. Oh, okay. Come on.
Then you do
41.4 feet. 15 meters.
That actually does. That actually.
Do you think it would just stay?
Yeah, it makes sense.
I don't know. Actually, it seems like it'd be maybe a little more.
Really?
3 floors could be a little bit more. Each floor. Oh, think about it. Okay, think about it. From the floor to the ceiling, how tall is it? If I'm about 5'2", let's just say 5'2".
I say 12 feet.
Okay, 12 feet. Plus there's. Wait, do a meter? So let's say. I would think it'd be taller than that. If this is 12, then the second floor is another 12, and then another 12. But then and then between each floor is about a foot. No, I'm saying it's about a foot in between each floor. From the floor to the ceiling. I'm like 5'2", and I feel like it's more than double me.
Yeah. So one.
You're exactly 5 feet.
Wait, do you have a meter?
We're comparing everything to.
What do you say?
This works.
Already got that.
Here. Charlie. This is the meter stick. Charlie.
All right, everybody got it?
Yeah. No. I think the first one. So you're in this on.
You always have a delay reactor.
608.
Yeah, it's just like 1 hour later.
All right, so what are we finding out about surface area?
It doesn't matter.
It's about.
Well, the weight, the weight is the only thing that matters.
Andrew,
Surface area doesn't matter?
No, I don't think surface area doesn't matter. I'm saying nothing like affected it.
Wait.
Only the weight.
It's about
Only
3
the weight
meters.
affected it.
Minus 2 inches. How much is 3 meters?
Nice, Rhea.
Wait, how did I got 3?
Okay, everybody have a seat, please. We'll all get the second part. All right.
No, I'm Brianne.
Brianne's mine, so
Wait. Okay.
Okay, I'm gonna go ahead and let you guys get started on the second one for those that are done, because they do need a little extra time. Arnold, let's get annoying. Let's talk very quickly. I heard Logan say that their group found no difference between surface area 1 and surface area 2. Is that what you guys got?
It's about exactly that. Yeah, it's probably like 35.
How are you guys
But they had different.
So what did you guys have for surface area 1 and surface area 2? The difference in
Floor is actually smaller.
what? Olivia, what did you guys do?
We're about to get the table floors.
Okay, this is up. I thought we were done. We have a whole nother lab to do. You guys got like 4 more minutes. So quick. Gotta hurry. It's not a whole nother lab. What are y'all doing? So tell me, you're not getting any different side or not? Yours is
Done. Thank you very much, sir.
That is really hard to show.
Right, so you're done?
We're done. We're done.
Are you done? Where'd you make that more quick?
Oh, really? Okay, cool. Hey, when is the game starting?
Okay, so the first 2 is 2.2.
Other ones,
Give me the metric stick.
Wait, Charlie, do you rate?
Okay, I have to go on because half are done in half hour, so everybody stop. Arm, I need you to have a seat, please. It's really good. They're being good.
No, it's 1.1.
No.
There you go. So, I want to make sure everybody has a good grasp of this before we go on. Did we get a difference in surface area when we tested surface area? Does a wide area require more force to pull than a narrow area?
Yes.
Okay, I think we can all agree on that. Now, what I want us to look at is how is that actually useful in real life. If you're not finished, please wait 3 minutes. I'll give you plenty of time to go back and finish. And about that, I gotta get this first and I gotta start your second lab because I don't have time for it either. Here we go. If I have a giant box in the garage and I want to move the box from one side to the other and it's too heavy for me to carry and I have to push it and I've got all this friction, it's just grabbing on the floor. If I turn it off to one side, will that be easier or harder? That would be easier. Sometimes they use pallets, right? And they put things on pallets. Or sometimes you see like, instead of dragging people through the snow, they put them on a sled or a sleigh. So instead of dragging them, they have these little runners. Those runners go through. That takes less force. It's a little bit easier. Y'all with me on that? Okay. What about when we added the extra weight? Did that slow it down or make it easier? Okay. It weighed it down a little bit more. So if you have a load that's dragging and dragging and dragging, one of the things we can do is take some of the weight out of it, right? That'll make it a little bit easier. Third thing we're doing is about texture. I think we can all agree that the smoother the texture is, the easier it's going to be floating. Why do they wax the floors? Why do they wax the gym floor? Why do they do all this? They want to make it as evenly and smooth as possible.
Why do they smooth out the seats?
That's a good example. Now, let's take a look at the second lab. You're probably thinking to yourself, yeah, but wouldn't it be easier just to roll it? If you stuck the thing on a cart or a wagon and you rolled it, that'd be a lot easier, wouldn't it? Or what happens if you put it in a boat and you float it? So I want you to compare today, I want you to compare sliding friction, rolling friction, and fluid friction. I don't care what you do. You make up your own lab. You design it, but I want you to compare two variables. Compare sliding and rolling, or compare rolling and fluid, or sliding and fluid. I don't care. You pick, you decide, you write the lab, you tell me which is which. Now, let me give you a couple quick ideas before you start. One of them is, First of all, what's fluid? Before we even go in, what is fluid? Liquids? What's it? Is liquid the only type of fluid?
Yes, no.
Is gas a fluid?
No.
It can be.
Can solids be a fluid?
Yes.
What about sand?
Ice can be a
If you
fluid.
take sand in an hourglass and the little clock, is that not a fluid?
Yes, it is.
Doesn't it flow? Why is it not a fluid?
A fluid is anything that can like.
But fluids are anything that move. Anything that flows from one place to the other. Boom. Gases can flow. Solids can flow if they're, small grains and things like that. So fluid does not mean liquid. People tend to use those terms inappropriately. Here is a compact disc with a balloon and a 2-liter bottle. I'm going to blow on this thing. Don't pick your mouth on it. Okay, now I'm going to put this on here. Screw it back on. Give me a clean place. Move stuff. There's this one. Okay, now watch. Whoa! It becomes like a hovercraft, doesn't it? Right? It floats on a pocket of air. That means air in this particular case is a fluid. Okay? I've actually been on a hovercraft one time. There was a hovercraft ferry boat. It would actually take, you park boats on or cars in there. You went across the hovercraft from one side of the island to another. Right? Huge, giant hovercraft. It's much more efficient than actually going through the water because air is less dense. So it's very cool. So what I want you to think about is, how can you test? Can you test sliding versus fluid? Can you test rolling versus fluid? You can use water. You can use wheels. You can take cars. You tell me what you need. All right? You have the rest of the class, about 20 minutes to design your experiment and test. Sorry for the rush, but we have short classes today. Okay? You have to tell me what you want, and I'll let you have it. Within reason.
No. Hovering is being still. No. Not no. But it's still not possible. But no is perfect. Denied it. Because the way water hits the ground isn't exactly. So you can have a hose and spray the same shape and spray the same power as the line hose, same shape, the same power.
If you guys are going to do watermelon, your water, why don't we put this down?
Same ground, same power.
Why don't you clear off some of those?
And then we can pull it.
You're saying like when they use a hose and then switch right
Yeah. What I would do,
That's
girls,
not hovering.
is I would take
That's not possible. They use 6 fire hoses on the edge of this, and it was only like 12 pounds.
just to fill up your.
Pound thing, and no.
Now, what are you guys using?
The wood and the water and the little car.
I don't need to show, like, I love what they do. What they do is like, they're weird. Like, the show's weird.
So what are you going to actually measure? The car going down the hill? I mean, the car going through the water?
Yeah.
So you're going
And
to
a lot of the stuff they do, they know, like,
You're making the boat?
how, like,
So you
you can use science to
compare the board to the car, right?
They just do it.
Just like the same thing. You have to make the car look.
Yeah. Okay.
Yeah, once you're filling up water. What do you guys do?
I don't want to tape it. Yeah. I don't get this though.
What are we going to do first?
Sliding fluid.
How would you roll the pump?
Board, you
So you want it in the water and then you
all
Yeah, and you take it out and you roll it on the table. And that's
or
Like, and they do so many things.
lots of different types of board.
we have to make
They never
Oh yeah, we should go stay with
this way.
True. They would give me if it was like they use exact stuff. Like, because so like in Halloween or they'll like replicas.
He's the smaller one. There. There's our car.
So can we take the bottom?
Yeah, take like a round.
Okay, just kidding. Oh, there's no.
As something this way. And the next episode might be a bit similar to Friday.
How far do we
And they don't make it. You guys know how that seems like
What way are we doing? Like this?
We do it like this. Wait, don't do it yet.
Yeah, we see the neutron thingy. The neutron. Yes.
Do you think that's good?
We're gonna roll it on the table. How long is it? Roll it on the
What's our procedure?
The first one.
Hey guys.
We should slide it down. Oh yeah, we can do that.
But that's not really gonna help.
We're sliding down.
I think it's good enough.
We're gonna get sand.
Yeah.
Okay. What is the procedure?
Yeah. Let's go have it. We need to wait, let's write it down.
Huh?
It's like draining through.
They look painted.
Huh?
It drains.
Yeah, but it fills up.
They feel this thing with the
Should we just like keep it going?
This is some of these are marked.
and this.
So, you don't really have more water.
So we're able to see this. Hey, can you stuff over there?
I need to cut off the
The weight should be the same, right? And air resistance should be the same. All your variables are So, how are you going to measure it?
With this thing.
You gonna use a ring scale?
The new thing.
You're looking for it.
Well, we're filling it with sand.
No, something's gonna do it. They said it has to
thing if it's not.
There's no wheels.
No, like, I mean,
Yeah.
so like they were just
But then this thing.
Oh,
I
yeah.
know.
We already did that.
99.
Annabette.
So I
Yeah.
can fold it for you like buy it.
Wait, we need to get started. We like to go
no,
right
they
Yeah, it doesn't, there's no
Okay.
Hey,
Like, it was.
So it's like to pull it like this. Do you have fans?
You want to hold back?
You're up, man. You got fans?
Okay, this is good.
No, we have to figure it out. Rhea, watch it. No, it's a drain and then it's, oh, in the water. Yeah.
So, let's just do this.
One. No,
Holy that,
point.
You can time it. If you
I think it's like
yeah, and then
it's like 0.4.
This is too much.
Triple beating down. Doing little things apart. Okay.
Now, do the same height. So you have to just think about, as long as everything is exactly the same. You can change this thing around and make it to where it's like,
Points nothing.
but bottom line, time slide,
Yeah, okay, I was 0.4 in the water. Now we have to flip it over.
about 12 minutes.
Starting time when it crosses the go.
Are you guys still doing the first
We need to train it now. I don't know. Okay, now let's pull it on the board.
It's 3.77 grams. So next one is left. 3.77 grams.
next class, I want to use it too. So you guys getting good at it?
Grams is small.
Where do we go after this?
No work. 4 to 5.
Oh yeah.
There's no. There's like no.
So what does that say? So you're gonna have to use something. So instead of it being like 1 on the
Yeah, like in the water it's like 0.4.
yeah, it'd be kind of interesting. Sure. It'd be kind of interesting is to test it just sliding too.
Yeah.
And see if that makes a difference. You don't have to do 3.
Yeah, maybe 0.1. It takes nothing.
Watch it.
Oh my God!
Did you watch it? Did you watch it? No. Great, you're supposed to watch it. I'm not gonna go like. Wait, Mark's singing.
Oh, I was thinking like I was turning it for a long time and just waiting. I was waiting.
It goes like up and down. It's like 0.2. Yeah, it's like 0.2 and then sliding. That was rolling. Now it is sliding. Sliding is rolling. Ready? Sliding is sliding.
Sitting at the front
Wait,
side
take
of
your pen. Wait, I'll take a picture of our cargo. Yeah.
Ready?
Yeah.
Go.
Sort of proud of this.
Ready? Set. Go. That's 90. No, we even need to do 90.
Try it.
What's
lighting?
Wait. Yeah, how many? How many do you have to have? Oh, the
So which was best? Rolling was better than the water?
It took like
ready?
Interesting.
like yeah, it was like rolling and then water and then sliding. Sliding was like
So, do you think it's just not a very aerodynamic boat?
I thought it was amazing.
I think, right?
Might be like
Is it always the same?
I got 63.3.
Rolling should be better?
And apparently this goes out. It's so sad. It's like the Titanic. I know. I kept
That's pretty easy. It's a pretty easy experience. But,
yeah.
yeah.
Iceberg. Here, go stand over there and I'll take it. Wait.
Teresa.
So you guys come up with it.
No, we didn't do fluid, right?
Did you get it? Oh, I need pictures for your book and Wait, is it moving crazy? I need pictures for your book. So,
And I
Let's all get around the car boat, guys. Or is it a boat car?
boat car.
It's a boat car.
It's about 19.32 grams. Wait, how much?
Okay, and then like the new thing is like,
Okay.
because there's no here it is. Put this on and turn it on.
Yeah, then it dies.
Then it
Okay, looks like
dies.
a lot of you guys are trying a lot of stuff, getting pretty close already.
Wait, it doesn't.
Charging the car too.
Ready? Ah!
No?
So then you can roll it. Roll it, let it, pull it.
Ew. It doesn't use any force at all.
I know. It's like 0.4.
Ew, it
Zinc.
It actually uses no name. It's great. Great.
I don't think you do it from like.
Hey, do me a favor.
Because real estate,
Carter.
Yeah, snake. Well, we supposed to get this wood.
Test the earring. It's either
I don't think it would have been here, so.
it's either nickel or like.
Oh yeah, I thought that.
Is nickel malleable? Because like they were like
Do you have paper towels?
So I never saw you guys do it.
We would have said
the fluid's 0.2. No.
What did you guys test?
I tested
Okay.
fluid is 0.2.
Let's take a quick summary here in a second.
Fluid is 0.2.
No, I'm not doing So rolling is more efficient.
Yes. It's our car.
Depends on the Who has me for
I'm running over. I'm coming.
It's allowed for it to be even in place. It's just introducing the
Well, there's something called rotational inertia. And rotational inertia. What's the term?
Oh, yeah. Well, and that's
But
no, he's saying
does this have more friction or does this have more surface area? Or does this have more surface area?
Let's get Stella. I think
They're exactly the same.
I'm skipping What if you're rocking it like you're
and how I look at it is if we made it roll and then
I'm gonna miss that car, bro.
if the weight is going down, even though it's not enough to pull the movie back up, it's still adding
This
more.
sheet we have to do
I think it's
for today? Yeah, do next class.
This one.
Yeah.
Oh yeah, we do have a sheet.
But this would be like I said, rotational
Oh, thanks
inertia.
for telling me.
Once I get this inertia into it, it wants to keep moving the rest of it slow down because it's so much more pressure.
My second
And
room.
that type of movement, slowing it down. Yeah, this doesn't matter. Okay, everybody have a seat, please. Let's go over the results of this very quickly. I want to show you a couple quick things as well that you can add in your conclusion. You did a very, very good job of doing a quick lab, so I appreciate that. Lots of creative ideas. Carter, you everybody ready? Girls at that table, have a seat. All right. Josh, tell me quickly what your table did and what your results were. Go ahead, tell me what you did. So they did rolling and they used what? Weights underneath it? Bring me a thing of colored pencils. A colored pencil drawer. I want to show that really quickly in case somebody else didn't try that. They used weights. I think this table over here used weights, right?
Yes.
And they rolled with weights. The colored pencil drawer, fancy. Now, the same thing you can actually use with colored pencils. This is a model of what the ancient Egyptians did. When the Egyptians were building pyramids, they used these giant blocks, and they took these blocks and they'd have to move them all the way across, you know, hundreds of miles. Well, take a 2,000-pound block and try moving it hundreds of miles across sand. It's very hard. But by putting logs under there, just the slightest little bit of push lets this thing roll really well, doesn't it? Now, even with that immense amount of force, they would have to take levers and push it forward, you know, a little bit at a time. But it made it so much more easy to do. And then what would happen if you take that same exact log situation here and then you put that in the river? Now what can you do with those logs? Now you float it down the river, so you're switching from sliding to rolling, and then from rolling to fluid. Who used fluid? What'd you do?
We made a car boat and pulled it.
Okay, they made a car boat. Hold it up, Zoe. And what'd you find out about your car boat?
It moves like faster when you roll it.
Okay, theirs actually worked better when it was on its wheels and it was going through the water. Now, I'm going to guess that probably not the most aerodynamic boat, right? And so there may have some resistance in the water, but still they have good data. They showed what they, in that particular case, it took more for fluid. Anybody else do fluid? What did you find out?
We found out that water makes it, like, for us, it's working reverse.
Okay, so what did you pull something through the water?
Yes, we pulled
Water, and it was almost weight.
yeah, according to this thing, it was like 0 newtons.
Okay, and then when you drug it, it was cycling.
We drug it again.
We use the situation like each of the log things, once they got it going, it'd be much easier to keep it.
Right.
Because there'd be like more resistance to the stuff.
Only a couple of people like pushing them, and then the other people would be at the back. And once it rolled off the last log, they would take it and bring it all the way to the front.
Okay. Another example that they did in the Egyptians is kind of interesting, is they would build this giant ramp up to the pyramid for whatever level they're working on. And they'd have to roll these things uphill, and imagine how much harder that would be. But when they got to the part where they wanted to put that big block right in place, they couldn't put the logs there anymore because it had. So instead of using a log, instead of using a river, they would pour oil underneath it. When you pour oil underneath it, we call that a what? Lubricant, right? And a lubricant is something that converts sliding friction to fluid friction, right? Now, let's take an example here.
Why in front of the pyramid, could they not just build a big like ramp under, like going down twice the size of the pyramid, and then they just let the thing roll, and then once they're
How would they get to the top of the ramp?
it would it would start from ground level. They would dig under like super far down, let it roll, and then it would roll all the way down and like go up the other side.
Well, that's kind of what they did, except for they built the pyramids like this, and it would be like, at first they're building it this high, and then they built another ramp that's this high. Every time they just built the ramp longer and bigger, and so eventually they got to the top. And then they had to take all the ramp.
Say in front of the pyramid.
Well, working is a big deal. All
I am very
right, let's take a look. Let's take a look at this one again. Hi, Jordan.
The water.
All right,
So you build it twice.
stay with me, please. Okay, water slide. Which type of friction are they using
Oh
there?
yeah.
Okay, that's an example of fluid friction. Ever get on a water slide where the water is not strong enough, or you lean on the part and it starts rubbing? Okay, and so when you get the sliding friction after you're used to the fluid friction, it really is bad, isn't it? It can give you like a little burn or something. Listen.
A while ago, probably about a year, this scared the crap out of my brother. He was on a water slide, but apparently he didn't weigh enough because there were these like bumps in it, and he would hit one and he would be airborne for like 4 or 5 seconds, and he would slam back down. And this happened 3 times because he's so small. And this was like the biggest water slide in Florida, and I could see him, and I was scared out of my mind that he was gonna fall off the slide because there was no friction.
I fell off the water slide.
Very good.
I'm like,
All right.
he's gonna die.
Got another picture. This is going to bring in some history. This is a picture of the Erie Canal. And the Erie Canal was built. You can see they have wagons and they have horses. Why put all the material in a boat and drag the boat through the water instead of just having a big wagon on a road?
Now you have wheels in both of them.
But
The wheels on the boat.
Why use the boat? And they found that fluid friction was better, more efficient than sliding friction. All right, so I want to make sure you guys get the difference. I don't think anybody in here would say that sliding is the best, right? Sliding is obviously worse. Well, last thing, hold on. Take a look at my engine block. What do you use to keep the engine from burning up? You gotta use that oil, you gotta use that lubricant to keep it from getting too hot. All right, make sure everything's put away. Everything back off your table. You can leave that. No, you guys leave that up. Go to fourth period.
What are we gonna get like a cheese?